in the system, and you have some contaminated waters to treat. I would add a fourth, a very typical, very typical characteristic of a treatment wetland. Because when you go to a treatment wetlands, you usually find scientists inside. This was to wake you up. Just a picture from Jan Wimmersar, a colleague of Vatka. This is a treatment wetland in the Czech Republic. I choose a local system here. It's a small system. You see it looks quite nicely, and you don't see that this is for treating wastewater if you don't look closely. A short introduction on different types of models that we can use in these systems. These natural treatment systems are rather complex systems. So we have a large number of processes that are going on in parallel. And most of the wetlands that have been used, most of the models that have been used are black box models. So people have been looking at the influent and at the effluent of the system and somehow correlated this data and derived some models from it. So, the wrong one. So something like this, you have a black box model. In this black box you can have some very complicated mathematical algorithms, like a neural network that's put in here. A lot of times you have, if you have along the flow distance, you have a degradation of chemical oxygen demand or total nitrogen. For example, here's two compounds that we want to remove. And you can derive some degradation constants from data that you measure. And these first order rate equations are most commonly used in designing these systems, but they have the big disadvantage that you derive the data from your experiments and that you cannot extrapolate your experiences to other climatic conditions, other types of wastewater, and so on. So you always have to make some preliminary tests to really design your systems on the spot. On the other hand, when we use tools like numerical models as a basic for design, so the idea is that we can better extrapolate to other conditions and to get more valid design tools. That's somehow the overall goal of modeling constructed wetlands at the end, to improve the designs that we have at the moment. So I don't have to explain the mass balance equation here in this audience, so I can move on. If I mentioned we have a lot of different processes in our systems, in our wetland systems, and we came up in one publication with a list of different submodels that we need to describe wetland processes in wetlands. First and very important is the description of the water flow. It's quite logical. Then we have to describe the transport of our pollutants, including adsorption, desorption processes. Then what's very interesting also to model is these biokinetic processes, the degradation processes, transformation processes of the different substances. We have a wetland, we have to look at the influence of plants. We have to describe processes in the subsurface, like particulate matter can reduce the pore volume available and finally lead to clogging. And we also have to include this reaeration process that's meant that the transfer from the gaseous phase into the liquid phase of oxygen, most likely. Yeah. When we look which of these submodels we can find in Hydrus, then we have the blue ones are the ones that are incorporated into Hydrus, in the general Hydrus model. The green ones, that's actually the Hydrus wetland module. So it's this description of the biokinetic of the processes, what's happening to all the substances in the wastewater or in other types of waters, and also this reaeration process. That's really included in this wetland module. What we cannot include, or what's not included up to date, is this clogging process, changing of hydraulic properties according to particulate transport. That's something we tried and try for a long time to get really a project running to really do it, but until now unfortunately we failed a little bit with this, but we'll keep going. and also the longer term influence of plants, like growth of plants, decay of plants, and release of substance, decomposition of plants. So this does not have a very big effect. It's not the top priority, but maybe sometimes later we also will look into this. The wetland module itself, just a summary, it was developed for subsurface flow treatment wetlands. That means we are in the subsurface. And this includes two formulations for this biokinetic model. There's one formulation that includes anaerobic and anoxic processes. And anoxic processes, just to mention it here, it's a terminology that comes also from wastewater treatment. And it means that only bound oxygen is available in the form of nitrate. So these are the conditions for denitrification, to put it in another way. And then we have another model, biokinetic model, that has been developed by several people working on wetlands modeling, and it's also named Constructed Wetland Model number 1. That also includes anaerobic processes. So, when you go into Hydrus in the latest version, you can, in the main processes, you can select these two biokinetic models from the user interface here quite at the beginning. You see that there are a different number of processes included in these two models and a different number of constituent substances that we consider. In this version that I developed in my PhD, in this biokinetic model, we have phosphorus included as compound, and the other one is sulfur. That has been, at some reasons, I will not go into detail, that would take too long to explain now why it's like this, but if you're interested, we can talk about it later. When you go to the Hydrus user interface, you see a lot of parameters here that are related to this constructed wetland model. Mainly describing all the stoichiometry of the reactions and the rate constants and parameters used to describe the reaction rates. But I will not go into detail here and show you all these models. You can find them in literature. It's described there. And I would like to show you some results that's more, to give you more idea what can be done with these types of wetlands. Just by chance, I removed a slide that I wanted to have include about the different types of wetlands. So now here are only the abbreviations. So we have, I make it without pictures now. We have what's called surface flow systems. These are, you can imagine it's a pond with plants. So you have a free water surface visible, and water is coming in on one side, going out on the other side, and it's treated there. So this is surface flow systems, and then we distinguish also subsurface flow systems where we keep the water level below the gravel level or the filter material level. This has the main advantage in a country like the Czech Republic, also in Austria where I come from, that you prevent these systems from freezing. So the danger of if you have an open water surface in winter, it's that it's freezing. And you should guarantee the treatment of the wastewater the whole year round. So these systems where you keep the water level below filter material are called subsurface flow systems, and there we distinguish horizontal flow systems and vertical flow systems. It's quite easy to distinguish what they are. Horizontal flow systems, you have a waterlogged filter bed, water flowing from the inflow to the outflow horizontally. You can imagine that the oxygen intake in such a system is rather poor because you have waterlogged conditions. And when you have to fulfill different treatment goals, that you also have to guarantee or have to use aerobic processes in your treatment like nitrification, then these vertical flow systems have been developed with intermittent loading of the systems. And the filters are batch loaded and water is percolating through the filter, and in between to the next loading, oxygen, air can enter the filter again, and so aeration is guaranteed in the system. So you can guarantee aerobic processes in these systems. Okay, because first example is about vertical flow constructed wetlands that we have been operating in our technical hall in our laboratory, where we can run these systems with real wastewater from a sewer that's running by. We can load them. You can see the typical cross-section design of such a system. You have 50 to 60 centimeter main layer, that's a fine sand. Then you have a drainage layer to get the water out, and you have some intermediate layer to prevent the fine sand to be washed out. It's quite a simple system. First, some pictures about some hydraulic simulations. You have a 6 hours time period in this picture. This is one loading. So there have been 10 liters per square meter for each loading. And then you see the effluent flow curves, volumetric effluent, fits quite well to the measured data. And also we did some water content measurements in different depths to check the hydraulic model. So this also worked quite nicely. A colleague of mine in her PhD, she was looking in the distribution of the microbial community in different depths of the filter. And this is some comparison of these different measurement methods she adapted to the filters to measure microbial carbon or microbial nitrogen, and they all somehow resulted in similar results. In the models we use COD, chemical oxygen demand, as a parameter where you can make a mass balance, and the simulation results also showed some quite good agreement. We also had it's not my presentation, 15 minutes. We also had an experimental system about 200 kilometers from Vienna that was outdoor, and what we did there, just briefly, we also calibrated the flow model, but we also looked at the temperature effect. Here you see the effluent concentrations for COD and for ammonia nitrogen over different effluent water temperatures, just to check the temperature model that's included, or the constants, the parameters included in the system. Next example, master thesis that's currently carried out by a student of mine, with the aim to verify the implementation of the new model in Hydrus. And what we did is there was a paper published by colleagues from UNESCO IG in Delft. They implemented the model in Aquasim, and they used data from Montana State University to make this comparison. So what they did in the US was they had these small pots. They have been batch fed, so the artificial wastewater they have been filled with artificial wastewater, and then they have been left in the columns for 20 days, and they measured different parameters. So it's a different type of system. And they have been planted it with different plants, and then they have operated this for several temperatures. So I just show you one slide with some results. This is 20 days, and they measured, for example, COD, ammonia concentration, and also sulfate concentrations. So this is 24 degrees temperature, simulation results without plants. So he still has to do something with the sulfur. It just is in the middle of the process, and I just wanted to include it here to show some of the pictures. Now to the first poster. A colleague from Torino, El-Nesr, he was with me the last 3 months, and he also wanted to look at horizontal flow systems and their behavior under different loading scenarios. The wrong one again. What we did here, we also went to the literature. We found a paper from Portugal where they made some lab scale experiments and loaded horizontal flow systems with different peaks. And yeah, with different, they had several lines, and then they added, there's some period with constant loads, and then there was a period with higher loads. And we used this data and tried to model this, and they also, in Portugal, they used also synthetic wastewater. We had to adjust the default parameters of the biokinetic model, a few of them. We had some problems that have been solved together with Jirka, that it was needed for this simulation specifically to have a very small maximum time step. The critical parameter here is the oxygen that's reacting very fast, And to prevent numerical problems, you have to go very low with the maximum time step, but now we have coupled this the time step adjustment with the concentrations in the system. So this should be now running more robust, this system. And we also spent several times about thinking about how this synthetic wastewater, how it's described in the paper, how this can be transferred into the different fractions of COD that we have in the model. So just what are fractions of COD that we have in the model? We assume that we have some parts of the COD that's very easily biodegradable, some parts it's slower biodegradable, not so easily. You can easily think of that you have short-chained molecules in your organic matter and you have longer-chained molecules. The longer-chained molecules have to go through a process before they are available as substrate for the bacteria. So there's a lot of small things needed to come up with this input data for the models. Next one. So for results for these two lines as presented for the COD, they look quite nicely. Yeah, you see also in the data they have published, they have quite some variations inside. But for COD finally we could make it. For ammonia nitrogen, he's not there yet. I should not say we because he's doing the simulations. He's not there yet, but the next step he couldn't carry out now is to also look into adsorption of ammonia in the system. So this is the next step that's planned, and we think that we can also make then the ammonia, match the ammonia concentrations better. Next example from Spain, collaboration with Spain with the Universidad de Castilla-La Mancha, that's south of Madrid in Ciudad Real. David Sanchez Ramos, also a PhD student there. And the problem there is somehow different. This is Spain and Ciudad Real is somewhere here, and in this area there's a natural wetland. That's a national park there. Tablas de Damiel. It's a very dry region here in Spain, and they have problems with the water tables in the wetland. So the idea is what they had to use effluent from treatment plants. You can see them marked here in this point here. You can have a better view on the post outside for sure. To polish the effluents from the treatment plant and use them as inflow water into the wetlands to guarantee specific water tables in the wetlands. So, and his thesis is about this whole system, and the modeling part was only a small part to estimate how much pollutants can be eliminated with horizontal flow wetland. Yeah, he came up with a standard design. The idea was to have one design of the wetland that can be put in all the different channels that are there, to have the same design to easily replicable. Yeah, we also included the influence of plants here, common reed, Phragmites australis, and yeah, he also had to change some of the default parameters, and yeah, he came up with about 2/3 of the COD can be removed in the systems, and about 40% of the ammonia nitrogen. These systems are designed with a very high hydraulic loading rate. That's a mistake. It should be hydraulic loading rate and not retention time, because there's quite a lot of flow through the systems that has to be treated. This was one of the main concerns. And this is a picture of the natural wetland, how it should look like when there's water. Last example I want to show you we go to Tasmania, southern tip of Australia, the island. It's a collaboration I had with CSIRO there, with Phil Smethurst, and they were looking at catchment areas, and they wanted to look at the runoff of the catchment areas. You have these small creeks here, and they wanted to look at the effect of riparian zones on the runoff. And this was when the project there started, and 4 years later you see that they planted these riparian zones there, and also they introduced a lot of measurement devices all around in the hillside. This is somehow the schematic sketch, that Hydrus was used to estimate the subsurface flow to the creek. There also you had to consider overland flow during heavy rain events. They carried it out with Excel spreadsheets. So this is something that we all know cannot be done with Hydrus. And at the end, yeah, they came up with quite some good estimations. For example, there's this subsurface flow, and for heavy rain events you also have an overland flow. And this matches quite nicely with measured data that you can also see outside on the poster, and also measured concentration of nitrate and simulated concentration of nitrate, they also matched quite well with measured data. So just to sum up, just different applications of these two biokinetic models. This model I've been working in my PhD was developed for vertical flow systems, and so we don't have anaerobic processes, so we can also only use this model for systems where there are where the anaerobic processes are not dominant. So the general aim of this constructed wetland model number 1 was then to come up also with a model formulation that includes all processes that you can go to both systems. And for the processes involved, that if you want to look at phosphorus, you have to use this model. It's clear because phosphorus is here, sulfur is in this model. And what I did not mention is that nitrification is modeled here in this model as a two-step process, because at the time I was working on my PhD, we had a system where we had problems with nitrite concentrations also that we were looking at. So, conclusions. They have been taken from a paper in Vadostone journal that I've published with Jirka last year. So basically this module is now in its second version available, and yeah, there are some things mentioned here, but there you have two more important slides. You can read this in the paper. There are some needs for improvement, because I asked all comments to come up with some suggestions what we need to improve the tool that we have now, and this Jirka is here now, so it's a good opportunity to show it. There are a few things that are very simple. I think with the new time step adjustment that we have done, I started with something that's very easy. Based on the experiences now with the new model, I think that's maybe then my work more, that I have to come up with a new standard set of for the parameters that's more useful than the one that has been published previously. And we had in the older versions, we had this limited outflow option that is not working anymore in the new version, because of some reason. That's something we have to look in also. And then we have a lot of things that's coming up here. These particle transport clogging processes, I mentioned it already, we tried to get projects to keep this running. Then one thing also in the wetland module, it's not possible up to now to use this physical non-equilibrium processes and this chemical non-equilibrium models together. And Anja in the next presentation will show you an example, tell you why it's really needed that both should be working. Also preferential flow is not more possible, and this is also for this type of systems Anja is working on, it might be more relevant. And some people always want to add some new processes, compounds in the biokinetic model, but at the moment we are rather fixed. We are fixed, not rather, we are fixed. And I have some ideas how this could be done also quite easily. And there are some that came from the hill slope application. This you can also find in the proceedings, because that's mentioned there from Fields Matters. There's also to end several things that only one root type can be fixed or can be done specified. And so this nutrient uptake he was using for this hill slope simulation, the old version of Hydrus, and the new version, this is also actually done. Okay, and with this, I would like to thank you for your attention. And I don't know if the chairman allows some.
No, of course. We have time for several questions. Okay, any questions, please?
Yeah, I was just wondering, you highlighted you can't model clogging or sort of preferential flow. How do we overcome that? Significant problems with channeling.
In a real system?
Yeah.
Now, in a real system, you have that. Usually, you cannot put the system out of operation because the wastewater is coming all the time. So that's really.
No, sorry, not in a real system. Obviously, a real system will have clogging and channeling.
Yeah.
So in the model, how do you overcome that difference? Is there any way around it?
No, in Hydrus you also have this. You mean what we plan to do, or?
Well,
currently. Currently, it's you're just assuming non-preferential flow, and so that these problems are not happening in the system. When these systems are working well, you usually don't have these big problems. Usually it should not make a big impact. Just to predict also overload of systems, and then when it really goes into failure of the system, so therefore it would be very important.
I have a question. So when I'm using Hydrus, I have maybe 10 parameters that I need to adjust, solid hydraulic parameters, solid transport parameters, and then maybe I'm working on 10. Here you introduce, what, 30 parameters?
Maybe more.
Maybe more. How can you start?
Yeah.
How can you deal with so much parameters?
It's a very good question. The basic idea in my PhD was that these biokinetic models use the same formulation that's used in activated sludge modeling. In activated sludge modeling, you have a lot of experience. These models have been introduced in the 1980s, and a lot of experience of using these models, and also some methods to measure some of these parameters. Those are most influential. And the idea was, and the experience also had showed, that once you get the hydraulic model or the flow model correct, that means the water flow is described correctly, the bacteria behave the same in the filter system as in the activated sludge system. So, and you can use these standard parameters from activated sludge models also for the systems and get some very good results. There are only a few, and of course sensitivity analysis have been carried out, and there are a few parameters that might be adjusted. For example, the decay rate of bacteria, so that they're not dying off that fast as in activated sludge systems, so there are some things. But this can also what the experience had showed that all the parameters that have been adjusted, you can also find it in the activated sludge literature, that there might be specific occasions where this is needed. And the others, will you mention your respirometry? The other thing what Anja did in her PhD, about 10 years after I finished my PhD, she made some respirometric, she developed a respirometric methodology for solid samples, not for liquid samples. And she compared the results for nitrification rate she measured in her respirometer with some data I have published previously. And the match of the nitrification rates that she came up from measurements and from that we used in the simulation was quite good. To say that this was somehow the proof that this assumption that you have somehow the similar behavior of the bacteria in both systems, treatment systems, it's the same, was somehow a good proof from an independent body.
Okay, thank you very much. Let's